Swayam Prabha. Digital India. Educated India.
Now we will discuss an important concept which we will revisit later in the context of circuits. It is linearity. Okay. Right now we have only discussed basic elements. So we will only discuss linearity of elements. Later we will expand it to linearity of entire circuits. Okay. So the question is, which of the elements is linear among the elements we have discussed so far and why? Now what does linearity mean? This basically means that its characteristics of an element which is linear obey superposition. And what does this mean? So if, let's say, you have a voltage V1 which results in a current I1 and a voltage V2 which results in a current I2, what does superposition mean? If you apply a voltage alpha V1 plus beta V2, which is a linear combination of these two voltages, this results in a current which is alpha I1 plus beta I2. That is, it is the same linear combination of the effects. Alpha and beta are the same. Okay. So this obviously means that if you double the value of V1, you will get double the current. If you make the value of V1 half of what it was before, it gives you half the original current and so on. Okay. Now of course I have taken voltages and currents here, but this is a general property that can be applied to systems. If you have certain excitations and certain responses, if the response is proportional to the excitation, it is linear. Or in other words, if excitation 1 gives you response 1, excitation 2 gives you response 2, then a linear combination of these two excitations should give the same linear combination of the two corresponding responses. Okay. So if this is not clear, it will be clear immediately after we discuss examples. So let's take a resistor. The voltage V and a current I are related by a proportionality relationship. This immediately tells you it is linear for those of you who are familiar with linearity, but we will go through it in any case. So what it means is, let's say when the current was I1, the voltage was V1. Obviously the resistor obeys Ohm's law and V1 equals I1 times R, and the current is I2, the voltage is V2 and V2 equals I2 times R. Now what happens if the current is alpha I1 plus beta I2? The voltage will be alpha I1 plus beta I2 times R. Basically it is the current times the resistance, which of course can be written as alpha times I1R plus beta times I2R, which of course is alpha times V1 plus beta times V2. That is, if we applied a current I1, we would have got a voltage V1. If we applied I2, we would have got V2. Okay. So if we apply a linear combination alpha I1 plus beta I2, we will get the same linear combination of responses alpha V1 plus beta V2. So a resistor is very much a linear element. Okay. So if you have a relationship that shows proportionality like this, it's a linear element. And an essential feature of this is that If I is 0, V is 0. That is, if the excitation is 0, the response would be 0. Okay. Now let's try this test on other elements. Okay, particularly voltage source and the current source, because they can be confusing. Sometimes you can apply a naive definition of linearity and say that they are linear, but they are not. Okay. So let's look at a voltage source. It maintains a voltage V regardless of the current I that is flowing through it. Okay. And the relationship graphically is given by a straight line. So if this is V naught, this will be V naught. Now sometimes this confusion arises that because the characteristics consists of a straight line, this is a linear element, but it's not. Okay, that we can check by trying to apply superposition. Okay. So let's say the current I is a particular value of I1, then the voltage V will be equal to V naught. Okay, because that's the property of the voltage source. It will always maintain a voltage V naught. Similarly, if the current were a different value I2, the voltage would still be V naught. And if you apply a linear combination of these, alpha I1 plus beta times I2, the voltage would still be V naught. And this is certainly not equal to the linear combination, that is alpha times this voltage plus beta times that voltage. Okay. So it does not obey superposition, which means that it is not linear. Okay. So don't be confused by the straight line in the characteristics. It's not linear because it does not obey superposition. And obviously the exact same thing holds for a current source. Again, the IV characteristics consists of a straight line this is I naught, but it's pretty obvious that superposition does not hold, because if you apply a certain voltage V1, you get a current I naught. If you apply a certain voltage V2, which is let's say double of V1, you will still get a current the same, which is I naught. Okay, you will not get double the current. So clearly this is also not linear. Okay. So it's pretty obvious. Everybody says that resistor is a linear element, and that's the correct answer. But sometimes some people get confused by the straight line characteristic of an ideal voltage source or an ideal current source. They are not linear because they don't obey superposition. Now they will be linear only if the value of the current equals 0. Okay, that's not a very interesting case, so we won't consider that. That is, if the current source is a zero valued current source, or if the voltage source is a zero valued voltage source, those would be linear elements. Okay. Now, what distinguishes the characteristics of a resistor, a current source and a voltage source, all of which are straight lines? So let me draw it here. A resistor has a characteristic which is like this. A voltage source has this characteristic parallel to the y-axis, and a current source has characteristic parallel to the x-axis. Now all these three are straight lines, but only this one is linear. Okay, that you can guess from the characteristic also. It's not enough for it to be a straight line, but it has to be a straight line passing through the origin. Okay. If it passes through the origin, it's a linear characteristic. If it's not, it's not. It won't obey superposition. Okay. So that's why I also said if the voltage source happens to be zero valued, the characteristic would be this, which passes through the origin. And similarly, if the current source is zero valued, the characteristic would be this, which passes through the origin. Okay. So otherwise, they are not linear. Now let's quickly look at the other two elements, the inductor and the capacitor. So the capacitor I is C dV dt, and if you have a certain current I1 because of a particular voltage V1, which is varying with time in some way, and another current because of another voltage waveform V2. These are all functions of time, although I am not showing them explicitly to be so. Then if you apply a linear combination of these voltages, okay, so let's say you make a linear combination of these as alpha V1 plus beta V2, you will get alpha V1 plus beta V2. This is the current, which because of the linearity of the time derivative, you can pull out as C times alpha times C dV1 dt plus beta times C dV2 dt, which of course is alpha times I1 plus beta times I2. Okay. So it's the same linear combination of I1 and I2. Okay. So basically the time derivative is a linear characteristic. So the capacitor is a linear element. Similarly, the inductor, which obeys this relationship, V is L di by dt, is also linear. Okay. I will leave it as an exercise for you to prove it. It must be again pretty obvious from the relationship. Okay. So both of these are linear elements. Okay. We will see later linearity of whole circuits and how superposition applies to them. And it's not just a property, it's something which can simplify the solution of circuits.